Our next guest is Jim Schmiedler, professor of aerospace and mechanical engineering in Notre Dame's College of Engineering. Dr. Schmiedler specializes in robotics and biomechanics. He builds robots and conducts research with biped robots, and part of the research makes a difference in the lives of people recovering from serious spinal cord injuries. So, Jim, first of all, welcome to Notre Dame Day. And I got to start with, when we hear the word robot, we usually think something out of a science fiction movie. But obviously, it's very real for you. And what are the challenges of working with robotics and the kind of exciting applications that you're trying to create?
Sure. So the killer problem for any mobile robot, even an autonomous car, is power consumption. And it's especially problematic with the kind of robots that I work on, which are robots that have legs. So I think in that previous segment you saw rock climbing, right? Mm-hmm. And if the terrain is uneven, having legs and arms to get over that uneven terrain is really advantageous. But the challenge for us is, how do we design these robots that are efficient and are robust in the sense that they don't fall over very easily? So those are really the big picture problems for mobile robots that we work on.
I know you were recently awarded an NSF grant for a project on the use of exoskeletons for people with spinal cord injuries. What can you tell me about that?
Sure. So I do work on walking robots in one regard and human walking in the other, and this exoskeleton project is really exciting. It brings those two threads together. We're working with a company out in California, a startup called Exobionics, and they have the most extensive FDA approval for use of exoskeletons in spinal cord rehab. And so these are essentially robots that you wear, aimed at helping individuals walk who don't necessarily have the strength or, say, the motor control to walk on their own. And so from the spinal cord perspective, if it's early on in someone's rehab, these robots can get them up and walking and get some of that sensation of the natural gait back that'll help activate the circuits in their spinal cord that need to be retrained in order for them to walk again. And then for someone who's had a complete cut of the spinal cord injury, these devices are really, at present, the only way we can get these people walking. And so our challenge as roboticists on this project is, how do we get the robot that you're wearing to recognize the intent that you have? So you want to speed up or you want to slow down. The grand challenge we talk about is, if you and I were walking in the mall together and I had an exoskeleton on, could you and I continue our conversation as we stepped onto the escalator seamlessly together?
Without you thinking about walking.
Right, without me thinking about walking, without you perhaps helping me by pressing buttons to change the mode of control for the robot.
Fascinating. So I know much of your biomechanics research is centered in healthcare, obviously. Not simply people recovering from spinal cord injuries, but stroke also, I'm told. So how does the research from one inform the other?
So in the robotics work, we take inspiration from human beings, because they're much more efficient and much better at walking than anything we build right now. But it flows the other direction as well. The analysis tools that we use with our robots inform how we process the data from the human subjects we're trying to help recover from stroke or spinal cord injury. And it also helps us develop maybe a new therapy regime. So I'm not a physical therapist. I partner with people who have those capabilities, who have a complementary expertise. And I think when we work together, bringing that robotics perspective can develop new ideas that we could test out with the humans, and new ways of quantifying human performance.
We've got about a minute left with you, Jim. Where do you hope to see this move in the next 1 to 2 years, or maybe even the next 1 to 2 decades? I'm not sure how broad that scope is.
So in the next couple of years, we'd love to see the exoskeleton control become what we would call more fluent, so more intuitive for a user, so that you could get more independence for someone who's had one of these injuries. In the next 5 to 10 years, I'd love to see more deployment of these units, walking robots for disaster relief, exoskeletons more commonly deployed for a variety of injuries from stroke to spinal cord. We need to make them lighter, we need to make them more efficient, and we need to make that control more fluent.
Excellent. Dr. Jim Schmiedler, appreciate your time. Another Notre Dame grad and professor doing great things in this world.